You ever stop and think about what it really takes to move something that weighs as much as a fully loaded commercial airliner? Not rolling it on wheels or floating it on water, but dragging it across solid ground with nothing but steel links and American ingenuity. Because back in the mid-1950s, there was a problem that made every engineer in the country scratch their heads until their pencils wore down to nubs. Picture this: a reactor vessel, solid steel. 200 tons of unforgiving metal that needed to move exactly 47 feet across a concrete floor without a single crack, without a millimeter of tilt, and without crushing the dozen men whose lives depended on getting it right. This wasn't some carnival ride or a piece of farm equipment. This was the beating heart of a power plant, and it had one job to do before it could ever generate a single watt of electricity. It had to get from point A to point B. Now here's where most folks would have given up before they started. The floor couldn't handle concentrated weight. The ceiling was too low for cranes. The doorways were already sealed. And every structural engineer worth his salt said the same thing when they looked at the blueprints. Impossible. But impossible is just another word for we haven't figured it out yet. The chain system didn't ask to be a hero. It was born out of desperation, sketched on napkins in a diner outside Pittsburgh, where 3 engineers sat until 4 in the morning drinking coffee that tasted like battery acid and arguing about physics. The desire was simple: move the unmovable, do it safely, do it precisely, and do it before the company lost so much money that heads would roll all the way up to the boardroom. You following me so far? Because this is where it gets interesting. The inciting incident came on a Tuesday. The vessel had been delivered 6 weeks early, which should have been good news, except nobody had finished the installation rails yet. The loading dock was torn up. The primary access route was blocked by another contractor's equipment. And the plant manager got a call from corporate saying if that reactor wasn't in position within 90 days, the entire project would be scrapped and the contract would go to a competitor who promised they could do it faster. 90 days. To move 200 tons across a floor that wasn't rated for the load through a building that wasn't designed for the movement using equipment that didn't exist yet. The decision came fast because it had to. Chains, not cables, not hydraulics, not some fancy European system that would take months to ship and install. American-made chain. The kind that had been pulling ore carts out of mines and hauling locomotives up mountain grades since before any of these engineers were born. Thick links of hardened steel that could take a beating and keep on pulling. But here's the first obstacle, and it was a doozy. Chain stretches. Not much, but when you're dealing with tolerances measured in fractions of an inch and weights that could punch through concrete like it was cardboard, even a little bit of stretch becomes a catastrophic problem. Every link in that chain would elongate under load. Multiply that by the hundreds of links they'd need, and suddenly your 47-foot move becomes 48 feet, and your reactor vessel slams into a support column that holds up half the building. The engineers knew this. They'd known it from the start. But knowing a problem and solving it are two very different animals. So they did what Americans have always done when faced with something that should be impossible. They grabbed their slide rules, cleared off a conference table, and started calculating. Think about the last time you had to solve a problem at work that nobody had ever solved before. That feeling in your gut when you realize there's no manual, no expert to call, nobody who's been there and done that. That's where these guys lived for 3 straight weeks. The first obstacle demanded innovation. They couldn't eliminate the stretch, so they had to account for it. Pre-tensioning became the answer. They'd pull the chains tight before attaching the load, measuring exactly how much each section elongated under specific weights. Then they'd calculate backward, determining how much slack to build into the system so that when everything was under full load, the stretch would bring them to exactly the right length. Sounds simple when you say it fast. But this was 1956. No computers, no digital sensors, just mathematics, experience, and the kind of stubborn refusal to quit that built this country. The second obstacle hit them during the first test pull. The chains worked, the tensioning system worked, but the anchor points started to fail. They'd bolted massive steel plates into the concrete floor, each one supposedly rated for 50 tons of lateral force. Should have been plenty. 4 anchor points, 50 tons each, 200 tons total, except physics doesn't care about should. When they started pulling, the force didn't distribute evenly. The front anchors took 70% of the load, while the back ones barely registered any tension at all. And at 70% of 200 tons, those front bolts started to sing. Not a good sound. The kind of high-pitched stress whine that means metal is about to let go. They shut it down, recalculated, redesigned the entire anchor system with progressive engagement, staggered tension points, and redundant safety catches. Added 2 weeks to the timeline, used up half their contingency budget, and still didn't know if it would work. Now I want you to imagine being the guy who had to sign off on the next test. Your name on the line, your reputation, maybe your career. 200 tons of steel that could break loose and turn into the world's heaviest wrecking ball. Would you have the guts to say yes? The third obstacle was friction. They knew it would be an issue, but they didn't know it would be the issue. Dragging 200 tons across concrete creates heat, lots of heat, the kind of heat that turns grease into smoke and makes steel glow if you're not careful. The first time they ran a full distance test with a weighted sled, they literally set the floor on fire. Not a big fire, but fire nonetheless. Enough to make the safety inspector threaten to shut down the whole operation, so they went back to the drawing board. Again, they tried everything: different lubricants, Teflon sheets, graphite powder, steel rollers that kept cracking under the load. For every solution they tested, they found a new problem. Too slippery meant loss of control. Not slippery enough meant destructive friction. The sweet spot was somewhere in the middle, and finding it required more trial and error than any of them wanted to admit. Are you starting to see why this wasn't just about dragging something heavy across a floor? This was about solving a dozen impossible problems at the same time, each one connected to all the others, each one capable of destroying the entire project if they got it wrong. The fourth obstacle came from an unexpected direction: politics. The union rep for the riggers caught wind that management was planning to use automated winches for the final pull. Automated meant fewer workers. Fewer workers meant layoffs. And layoffs meant a strike that would shut down not just this project, but every job the company had in 3 states. The chief engineer found himself in the union hall on a Saturday morning, explaining to 24 skeptical workers why the chain system needed both their skills and the mechanical assist. It wasn't a speech he'd prepared. It wasn't in any engineering textbook. It was just honest talk about how the mathematics demanded precision that human hands alone couldn't guarantee, but also required human judgment that no machine could replicate. Somehow it worked. The union agreed to a hybrid approach. Experienced riggers would control the operation, but they'd have mechanical backup if things started to go sideways. It cost the company an extra $12,000 in labor. It added another week to the schedule, but it kept everyone working and it kept the project alive. Beginning of the end came on day 83, 7 days before the deadline. They'd solved the anchor problem, managed the friction, calibrated the stretch, and gotten everyone on board with the plan. The reactor vessel sat on a custom-built sled, chains attached at 8 precisely calculated points, every system tested and retested until the numbers said it would work. The plant manager stood in the observation room with his hand on a red phone. Direct line to corporate. 1 call, either way. Success or failure. 90 days of work coming down to the next 6 hours. They started the pull at 6 in the morning when the concrete was coolest and the building was quietest. Inch by inch, slower than you walk, slower than you breathe seems like. Every foot of movement took nearly 8 minutes. The chains sang under load, a deep humming that you felt in your chest more than heard with your ears. Hydraulic winches whined. Steel scraped against concrete despite all the lubricant, and 200 tons began to move. First 10 feet went perfect. Tension readings exactly where they should be. Temperature rising but within acceptable range. No anchor movement, no unexpected sounds. Then came the crack, not from the chains, not from the anchors, from the sled itself. A weld that had passed every inspection suddenly decided it had enough. A hairline fracture appeared in the main support beam, visible to the naked eye, growing longer with every inch of movement. This is what they call the moment of truth. Stop the pull, and you might never get the momentum back. The sled could settle into the concrete, seize up, become impossible to move. Continue the pull, and that crack could propagate, the beam could fail, and 200 tons could drop 6 inches onto a floor that definitely wasn't designed for impact loading. The chief engineer made a call that still gets debated in engineering schools. Keep pulling, but shift the load. Redistribute the tension to take weight off that beam. Do it on the fly. Do it without stopping. Do it without any guarantee it would work. The climax came at the 30-foot mark. The crack had grown to 18 inches long. The backup beam was taking 80% of the load. Temperature gauges were reading 15 degrees higher than the safety margin, and they still had 17 feet to go. Every person in that building knew they were watching something that could either become legendary or catastrophic. No middle ground, no partial credit. The chains would either finish the job or they wouldn't. The hydraulic operator, a guy named Frank who'd been pulling loads since before most of the engineers were born, made a choice without asking permission. He'd noticed a rhythm to the sled's movement, a slight hesitation every 4 feet where the concrete floor had expansion joints. In those moments, the tension dropped just a hair. Not much, but enough. Frank started timing his pulls to match those moments. Acceleration when the load was lightest, coast when the resistance peaked. It wasn't in the plan, it wasn't in the calculations. It was pure feel, the kind of knowledge that comes from 30 years of listening to how metal talks when it's under stress. And it worked. The crack stopped growing at 20 inches. The temperature stabilized. The sled kept moving, 35 feet, 40 feet, 43 feet. The observation room was dead silent, except for someone's watch ticking and the scratch of pencils as engineers documented every reading, every measurement, every detail of what was happening. 47 feet. Exactly. The reactor vessel settled into position with a sound like a giant taking a breath and holding it. The chains went slack. The winches spun down. And for about 5 seconds, nobody moved because they couldn't quite believe they'd actually done it. The aftermath was quieter than you'd expect. No celebrations, no champagne. Just a bunch of exhausted men standing around a 200-ton piece of equipment that was now exactly where it needed to be, checking and rechecking the measurements to make sure it wasn't a dream. The sled beam held together just long enough to remove it from under the vessel. It broke clean in half when they tried to lift it onto the salvage truck. 6 more inches of movement, and it would have failed under full load. 6 inches between success and disaster. That's the margin they'd been working with, and nobody knew it until after. The final inspection revealed something interesting. The chain system had stretched exactly as calculated. The anchor points had held with a safety factor of 1.2, which was tighter than anyone wanted to admit, but still technically within spec. The floor had developed 3 small cracks that weren't in the original survey, but structural analysis said they were cosmetic, and the total movement distance was 47.03 feet, 3/100ths of a foot off perfect over a pull that took 6.5 hours and involved more variables than anyone could count. Frank got a bonus check. The chief engineer got a promotion. The union rep made sure everyone knew that human skill had been just as important as the fancy calculations. And somewhere in a file cabinet in Pittsburgh, there's a set of blueprints with coffee stains and pencil marks showing every iteration, every failure, every solution that led to moving 200 tons across a floor with nothing but chains and the kind of determination that doesn't know how to quit. The reactor went online 4 months later and ran continuously for 38 years before being decommissioned. During that time, it powered 600,000 homes, and not once did anyone who flipped a light switch think about the chain system that made it possible. That's how it goes with the infrastructure that holds civilization together. Invisible until it isn't. Taken for granted until something goes wrong. But the engineers who worked on that project never forgot. Some of them went on to move even bigger loads, design even more complex systems, tackle even harder problems. And every single one of them kept a link from those chains somewhere in their office, or their garage, or their workshop. A reminder that impossible is just a word. And sometimes the simplest tools, the oldest methods, and the stubbornest people are exactly what you need to drag the future into place 1 ton at a time across floors that were never meant to hold it, but did anyway because someone refused to accept that it couldn't be done.